Okay, now we're on to a grown-up example of using the binomial. The reason why this is more demanding is that this now is not a 1. And the formula given, okay, so the formula that you get in the formula book is this one, okay, which assumes that you're starting with a 1 here. So immediately I have to do something about this 4. I'm not allowed to have a 4 at the point where I'm allowed to do I have to do the approximation. So what am I going to do? Well, let's just have a look at this bracket, 4 minus 3 x. Okay, well, 4 minus 3x I want to write as a bracket with a 1 in it. So how am I going to make that happen? Well, I could write the 1 down and then I could multiply by 4 afterwards, couldn't I? Well, what else do I need in the bracket? It's going to be minus, but it's whatever that when you multiply it by this 4 ends up being this minus 3x. So therefore this has to be 3/4 of an x, because 4 times a 3/4 of an x does equal a 3x. And I'm taking it away, so the minus is right. So I drag out this factor of 4. Okay, well that's fine if I just want the bracket of 4 minus 3x, but the whole point is I've got a power of that bracket. So I'm going to put a half on here, okay? Now the beginner's error is to just put a half on here and carry on. That's completely wrong, because if I put the half on this bracket, it only applies to the bracket. But this thing, this original bracket, was the whole of this. So these squaredy brackets, okay, are really important. We're doing the whole expression to the power of a half. So the power of a half applies to the 4 as well as to the bracket. So my next line is 4 to the power of a half times bracket 1 minus 3/4 of an x to the power of a half. And this 4 is going to be affected. In fact, 4 to the power of a half is 2. Okay, now I can do the normal binomial thing. I'm going to do a big bracket. Now, this 2, I'm going to include it on every line. I mustn't forget to multiply my final answer by 2 at the end. But at the moment, I'm not very interested in that 2. I'm interested in expanding this. So I've only got to go as far as x squared this time. So it always starts with a 1. I've now got a 1 here, so that's correct. Remember, the next term is n times x. Remember, I'm still using this formula, so I'm going to be doing n times x and then n times n minus 1 over 1 times 2. So my n is a half, and instead of an x, I've got this minus 3/4 of an x. Not this minus 3x, that's gone. I'm now dealing with this bracket as it is now. So the nx term is going to be a bracket for n and a bracket for x. What's my n? It's a half. Okay, what have I got instead of an x? I've got this minus 3/4 of an x. So that's my next bit. Okay, you do realize it would be totally insane for me to try and simplify that at this stage. I'd do a totally unsimplified version and then I simplify it in stages. So the next thing was when I have the n times the n minus 1, so something times something divided by 1 times 2, and then I have the x squared, or whatever I've got instead of x squared, plus dot dot dot. Okay, I only have to go as far as the x squared term, so I can stop. This is not an equals, it's a plus. So what's n? A half. What's n minus 1? A half take away 1 is minus a half. Over 1 times 2, what have I got instead of x? Minus 3/4 x squared. Okay, so am I going to try and deal with the 1? No, I'm not stupid. I'll leave the 2. I'm going to leave the 2 alone. Okay, I'm going to do 1. This I can simplify. 1 minus 3/8 of an x. Okay, this I should not try and simplify. I'm going to do it in stages. Okay, and then I'm going to have one final stage when I can take the 2 into account as well. So I've got a half times minus a half times divided by 2. So I can do that on my calculator if I like, or I can do it in my head. It's minus an eighth. Then I've got a negative number being squared, so that's actually going to end up being positive. It's going to have x squared, but the 3/4 is squared as well, so it's 9/16. Okay, and that's plus dot 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 inside the squaredy brackets. Now finally I can take the 2 into account, I can do this multiplication, and I can get my final version. 2 times 1 is 2. 2 times minus 3/8 x is minus 6/8 x, but that's minus 3/4 x. Okay, again, your calculator can help here. Okay, 2 times minus an eighth times 9/16. Okay, well 2 times an eighth is a quarter, so I can use that to simplify. This is going to be minus 9/64 of x squared plus dot dot dot. Okay, now the question doesn't ask me, but it's always a good question, what's the validity? So the validity, remember, in the formula is that the modulus of x has to be less than 1. But I haven't been using x as x. What have I been using x as? I haven't been using x as minus 3x. I didn't do the expansion on that form, remember. I did the expansion on this form. So this is the form that I look at for my validity. Modulus of something is going to be less than 1, okay, but it's not x, it's not minus 3x, it's this minus 3/4 x. The modulus of that has to be less than 1. Well, the modulus zaps the minus, and I don't care about that, but I do have to divide by the 3/4. So that gives me that x, modulus of x, I should say, is less than, divide by 3/4 gives me 4/3. Okay, good. So I've done part 1. Part 1 was finding the expansion, but part 2 says, hence use a suitable x to find an approximate value for 3.97. Sorry, the square root of that. Well, the point is that if x is inside this range of validity, if x is small, then x is going to be small, x squared is going to be very small, x cubed and higher powers are going to be smaller than that. So what we can actually say is that 4 minus 3x to the power of a half is approximately equal to 2 minus 3/4 x minus 9/64 x squared. Stop. I'm missing out the x cubed and all the other terms, but if x is small, so for smaller x, if x is small, then the x cubed and x to the 4 and so on terms are going to be really, really tiny, and they're not going to matter much. Okay, so that's the idea we use when we're doing an approximation. Okay, so when we're using this to do an approximation, which is what we're doing in part 2, okay, we need to be dealing with both sides. Okay, we need a value of x to put into, this is the approximate side and this is the exact side. So this is the expression that I'm approximating. This, if I stop at x squared, is just an approximate value for it. So I need a value of x to deal with, to put into here, but that comes later. The first thing to focus on is what value of x do I need to put in here. Okay, so I want to be talking about the square root of 3.97, and I want that to be related to 4 minus 3x to the power of a half. And they're telling me to invent an x that will make a link between these two things. Now in this particular thing, 3.97 is just a little bit less than 4. So I can choose an x and it's going to end up being a small x. So these two things are actually the same. So if I want to find out about the square root of 3.97, I can say the square root of 3.97 is bracket to the power of a half. Remember, a half, power of a half, causes a square root. So this is going to be true when 3.97, as long as I make the 4 minus 3x equal the 3.97, it's going to work, okay? Because the power of a half is a square root. So 3.97 has to be 4 minus 3x, okay? So, a little bit of solving equations going on here. This is a bit less than 4. In fact, my 3x would have to be 0.03. This is 4 with 0.03 taken away from it, leading to x equals 0.01. What we're doing is we're taking this is a GCSE linear equation, okay, and we're solving it for x. And the answer for x is 0.01. And that is a small value for x. Remember, my approximation will be valid for a small value of x. Great, so for this value of x, the exact side is exactly what it ought to be. So 3.97 is exactly, square root of 3.97 is exactly what I get when I substitute my 0.01 into the exact side. So therefore, an approximation to this is what I get when I put my 0.01 into the other side. So 2 minus 3/4 of 0.01 minus 9/64 of 0.01 squared. And of course, I can do that on a calculator. A good trick is to use a memory or even just the answer button. If I do 0.01, and press equals, okay, now it's got that stored as the answer. So in order to substitute the answer in here, I need to do 2 minus 3/4 of the answer minus 9/64 of the answer squared. So 2 minus 3/4 times the answer minus 9/64 64ths times the answer squared. Okay, so that equals, okay, so this equals 1.992489 equals 1.992489. Okay, it says give an approximate answer for the square root of 3.97. Now, it's always advisable to give lots of decimal places on these, because of course what you could easily do is just do the square root of 3.97. I mean, that's completely missing the point of the question. The question doesn't want you to do this. Okay, all right, anyone could do this. All right, and it gives us 1.9924. Oh, look, it's very similar. Not 1.992485.9. So in fact, these are slightly different answers, but I've rounded this so much that actually, if I need to go back, okay, I need to do those last two steps again. If I really want to convince the examiner that I did this without cheating, I need to show that 95938 at the end, okay, whereas the exact square root, well, the direct square root calculation gave me 5885 instead of 5938. So you can see this method, this was really great. I mean, what before calculators could do square root of 3.97, this was a good way of getting approximations. Okay, it may be a little bit old-fashioned now, but in fact what your calculator is doing when it does these calculations, it's not magic, it's finding out a lot of these calculations. It's doing by finding series approximations, much as we're doing here. So in fact some of this theory is what underpins some of the methods the calculator uses. Anyway, that's a grown-up example of a binomial, including an approximation at the end. There's another one of these to do in the booklet. Okay, you might want to have a go at that by yourself, but there will be another video showing you how to do it. But have a go by yourself first.